Hello, everybody. This is Kevin Sloan, Director of the University Rover Challenge. Glad to be back with you again. I know we couldn't be together out in the field this year for the finals competition, but glad that we're able to connect with you this way. Have another exciting presentation today. I'm joined by Dr. Heather Smith. Heather is our lead science judge for URC. She has been a URC judge since the beginning back in 2007. So she brings a wealth of field science and astrobiology background and knowledge. And it's always exciting to see how she's able to work with the teams. Heather's going to give a little bit of a background of the science mission at URC, a little bit of understanding of what we're looking for, how that fits in with the context of astrobiology, Mars exploration, what NASA might be looking for within their own missions, and again, how that applies to the team so that you all have a little bit better understanding and help you prepare for future year's competitions. So at this point, I'll turn it over to Heather, let her introduce herself and jump into her presentation. And hopefully we'll have a couple questions afterwards. Heather, take it away.
Thanks, Kevin. So I'm Heather Smith, like Kevin mentioned, and I'm going to go over the science mission. I'm currently a researcher at NASA Ames Research Center. I work in astrobiology and planetary science. My doctorate is actually in biological engineering, which is not usual for the planetary science or astrobiology field. Most of the degrees are in geology or astronomy or physics. So the biological engineering is a little bit different perspective, and I work on life detection instrumentation. In particular, my doctorate was for Mars, and then I switched towards Europa, and now we're working towards Europa and the lunar surface. All right, so this is related to the 2020, 2021, and 2019 URC science mission. So specifically what it is, it's an in situ life detection mission. What that means is we want the instruments, or we want the teams to be able to analyze the data coming back from the rover and tell us if a sample has extinct life in it, extant life, or no life. Okay, so that is the goal of this competition. Now, it's a very hard goal to accomplish in that there's not really that many life detection instruments available, like currently on the market. So most of the teams, they have to take techniques from microbiology, techniques from spectroscopy, a lot of different techniques to combine the ultimate or desirable payload package. All right, so I'm going to go ahead and start with a little bit of background. So for the science mission in particular, we don't really care that much about the engineering. We don't care how fancy or how nice the rover looks. We just want to make sure the rover has the science functionality and science integrity that it needs to. So if you have a really spiffy looking rover, but it can't do science, that's not really very good. If you have a pretty beat up rover, but the science is good, that's even better. And like it says here, if your rover became a lander, you could still do very well in the science task as long as you could explain your science well enough to us. Also, if you had a perfectly operating rover, but you didn't know the science, you would score very low. So again, the science matters for the science mission. So if you're at URC and your rover seems to, let's just say it's going to break down. A lot of the rovers break down, probably at least a third of them have some mobility issues somewhat during the competition. Go ahead and show up at the science because you could still get some points. All right, now let's go to the 2019 competition. Most rovers either had a functioning sample collection system or functioning payload or functioning communications, but not all three. There were maybe like 2 to 3, maybe 4 rovers that had all their systems working. Most of the time, some system was broken within, some system was broken for the rover for the science mission. Now, generally it was on the first and last day. The middle day competition, by that time, the rover may have broken the day before and they fixed it, or they got the comm issue solved. And by the third day, they may have already competed in some of the more challenging, physically mobility challenging tasks. And so the rover could have broken through that. So the second day generally doesn't have as many mobility issues than the first and the third day. Okay, and then for 2020 and 2021, the science mission is going to be very similar to 2019. There's going to be very few exceptions, and one of them is that we're going to put out more rocks. So last year we had 2 rocks to identify. This year we will have at least 4 rocks per site. And when I say rocks, they could be coprolites, they could be fossils, they could be just sedimentary stratigraphy. They could be a number of things. And the rovers need to say, is this extant life, is this no life, or is it extinct life? Now, the only way the rocks are going to be extant life is if I put an endolith or a hypolith out there, and you're going to be able to see the green stripe, or you're going to be able to see the colonies on the bottom of the rock. Okay. Other than that, it'll be either extinct life or no life.
So Heather, if I
Also,
could just
go
jump
ahead.
in quickly there, because I was having
Sure.
a conversation recently with a couple of the other judges, and we are talking about how interesting it is when engineers and scientists have to work together, and the engineers have to understand how to get requirements from the field scientists. And there are some things you were going through there, and there may be some teams that haven't been able to attend the competition before that may not have a field scientist working with them yet. So I think something that I would recommend to the teams, as you were listening to Heather there, she was listing different types of rocks. Certainly, some of the rocks like sedimentary, we've all heard those rocks. But some of those other rock types, if those were new terms for you, it probably means that you need to find a field scientist to start supporting your team. And similarly, Heather was saying extinct and extent life. And if you didn't catch the difference there, that those are different words with different meanings. If you thought Heather was just repeating the same word twice with a different inflection, again, that's another indication that it's important that you get the right scientific knowledge base on your team. Because again, you can be a great team of engineers, but if you don't have that scientific knowledge base in your team, you just won't be successful in this task.
Yeah, thanks, Kevin. That's a really good point. So at the beginning of URC, most of the teams were all engineers, and they did pretty poor on the science, and their excuse was they came from an engineering school. And our reply is, we don't care. You need to have the science. So even if you have to go to another school to find a scientist, that's fine. So that's usually mainly with the international schools. Their schools specifically focus on engineering or focus on science. With the U.S. and the Canadian colleges and even the Indian colleges, you can walk over at your university, you're going to have a college of science. I would recommend finding somebody in the biology department or in the geobiology department, somebody that focuses on geomicrobiologist or geomicrobiology. I would find one of those scientists. If you can't find any scientists, you can do the literature search yourself. Go to scholar.google.com, and in the rules, there'll be specific words like extinct life, extant life. You'll need to know what those definitions are, and you can find that again through the literature search. And also, you need to know some general paleontology terms for the fossils. So the fossils fall under paleontology, and generally the extant life falls under microbiology. So if you can have a microbiology, a paleontologist, geomicrobiologist, that's perfect. If you can't find anybody to join you, then you'll have to do the research yourself. But we expect for you to come to the competition with some background knowledge from reading research, peer-reviewed journals and talking with your professors and your colleagues in the College of Sciences. Okay, so thanks for that good point. Okay, now back to the competition. So for 2020, the science. I want to say we also don't expect the teams to be 100% science because generally the scientists and engineers are trained differently, and this may be a little bit of rude. I hope it's not too rude, but the science teams generally don't do as well at the engineering, and pure engineering teams don't do well at the science. You need a mix. Okay, so for 2020 and 2020, now 2021, the science mission will be very similar to 2019. 2 exceptions again. There will be more rocks to identify, and again, it could be like a coprolite, which is sedimentary poop. It's basically fossilized poop, and you can look that up. There might be some other fossils that we would find in Utah, like fish fossils, dinosaur bones, stuff like that. We don't expect the fish fossils or the dinosaur bones to be on Mars. However, they're good examples of a fossil. So, okay, and then the second thing is the soil samples will be spaced farther apart. So last year we put them about maybe half a meter apart each sample, and that wasn't far enough. Some of the samples got driven on by the rover, and that kind of messed up the cleanliness of the sample, so we had to clean them up, and we did clean them up after every single team. So this time we're going to put the samples a little bit farther apart because a team would get deducted if they drove over the sample instead of between the samples. So that's the only difference. Also, we change this competition every year, usually, and when about half the teams or more can successfully complete the challenge, we'll change it for the following year. Last year, less than half the teams were, and so 2019, less than half the teams were able to successfully complete this. So it's the same for this year. Since this year's canceled, we're just transferring it over to 2021. Okay, here are some of the past URC science tests. And you can go into the URC website and search the rules and read the requirements if you want for each of the past ones, because 2020 is a combination of 2007 competition, 2008, 2009, and 2019. So it's a combination of the first three and the last competition. So you can always read those and see what we suggested for your instruments on board there. Okay, so the way we judge it, we start judging the science at the SAR, the System Acceptance Review. That is limited to 1 page, and it's the last page of the SAR. And then we also watch the video. So we used the SARs in 2019 to be able to determine the sample size of the sample container to use at the competition site. We'll be using the exact same sample containers we used last year, which is approximately 21 centimeters deep and I think 25 centimeters wide. Then the rover should include, the SAR should include the science payload, why you choose them, how they'll help you with the tasks, and how you will be able to distinguish between extinct, and absence of life. And you also, if you're going to have any hazardous chemicals, need to address your hazardous chemical plan. So some definitions for the science mission that I have here is a definition of extant life, extinct life, and absence of life. These definitions are how we'll be using and what we use for the science mission. So extant life, of course, is alive now or metabolizing or very recently dead. So like dead biomolecules such as PLFAs, if they're still intact as fatty acids, those would be considered extant life, okay? If they are fossilized, meaning there's no metabolic, they're not, the biomolecules broken up or degraded, that would be extinct life, okay? And if neither of those are present, then there's absence of life. And you may ask, how can we get absence of life? Because everywhere on Earth, with the exception of molten lava, has microbes in it. The way we do that is we actually bake the soil at 500 degrees centigrade for more than 24 hours, and we get all of the life out and all of the organics out of the soil. That is what we call the absence of life sample. Okay, so the most common mistakes for the URC2020 SAR is I don't want to say most, but a lot of the teams did not distinguish the difference between habitability and life detection, and there is a difference. This competition is not a habitability competition. It is a life detection competition. Okay. What I mean by life detection and what we mean is what I just described on the slide before. We want to have biology and biomolecules. Soil science doesn't help at all in life detection. It's habitability, but I'll explain that further. So another common mistake that most teams did was using inappropriate reference sources or not using references at all. Some of the teams used Wikipedia. Wikipedia and websites are not valid references because they're not peer-reviewed, unless the reference is from a federal agency, and in that case, it is vetted before the information is put up there. Wikipedia in particular can be changed very easily and does not always have accurate information. So if you use Wikipedia as a reference, that was not a good thing to do. It's better to have no references than to have Wikipedia as a reference. Okay. Then explaining how the team is going to select a sample. A lot of teams did that. That was a waste of space. The teams don't actually get to select the sample at all. We provide you the samples. So while their selection process wasn't wrong, it was just not needed and wasted space on the page that you could have provided better information on the actual assays that you chose. Then another thing, and this got you not very good at all, is teams that claim the habitability measurements like soil temperature, relative humidity, pH, and atmospheric gases, and any other environmental conditions. So those are like conditions that have nothing to do, conditions that aren't life detection. They're more of environmental habitability conditions. Those are all habitability conditions, and they did not help you at all if you had no life detection. Now, habitability measurements are great and wonderful to include as long as you have additional life detection measurements, because they can put the life detection measurements in context. But without the life detection measurements, and some teams only had habitability, they would do very poorly. Actually, they would probably fail the competition. So, again, if you claimed habitability measurements were life detection techniques, that was bad. And if you failed to actually include a life detection method. Most teams that did well had multiple life detection builds. They also had a lot of their instruments they built themselves. So that was some good things. Most people had multiple instruments and multiple life detection techniques or assays. Okay, some more mistakes. People would include a microscope on their payload, but they would say they're just going to use it for soil texture and say how soil texture would detect life. Again, that's pretty bad. You want to make, if you can use a microscope for soil texture, but then you also might want to mention, oh, and by the way, if there's a microbe moving across the screen, we would be able to see it. So they would mention a microscope on the payload, but refuse to mention anything biology related to it. So that was a pretty common mistake with about 4 or 5 teams. Okay, then the other mistake that was made is the method might have been unrealistic to work in the time given. So for example, the Power DNA soil kits, those take like 20, 25 minutes to work, even when you use the large amount, the 10 grams of soil. The competition is only 30 minutes long. That's not enough time for you to go out, collect the sample, and use those DNA extraction kits. So we didn't deduct points for that, but as long as you could adequately explain how the DNA method worked and why you chose that. But if URC 2020 had gone through, the team would have got a note from me or from one of the science judges that said, look, although your technique is valid, it's not going to work in the amount of time. You need to do X, Y, and Z to modify it. Okay. We didn't send these out this year because we're not having the URC competition, but there were about 3 teams who used a DNA soil power kit, and there's no way there's enough time to use those during the competition. Okay, so again, searching for conditions favorable to life is not the same as searching for life itself. So you need to measure some sort of biomolecule or some sort of biology. And then, again, this is just saying if any of the 36 teams that were invited to URC had a bad science plan, to me that means no life detection or life detection that doesn't work in the amount of time given. We notify the teams to let them know that their science needs to be improved prior to the on-site competition and the suggested modifications we expect to see in the science plan, which is the next document. Okay, so after you're selected through the SAR, and if you're coming to compete, I think it's in the early May timeframe, your science plan is due. Your science plan is limited to 5 pages, and usually the teams that are selected have already been given feedback from us on what they need to change, and they'll submit their science plan, and most of them are done pretty good, but here are some of the mistakes that are still made. Again, not using references when one should or inappropriate references. For some reason, people think Wikipedia is a reference. It is not a good enough reference. Okay. Also, making false claims and then using a website to back up the claim. That's pretty bad. When you say something like, you know, the surface of Mars has, you know, a pH of 2, and then you cite some kind of conspiracy theory as your reference. So this happened one of the years where somebody said, I don't remember what, oh, the life was found on Mars. Okay, let me just tell you right now, life has not been found on Mars. Okay, but they said life had been found on Mars, and then they used some Berkeley philosophy professor that had nothing to do with the field as their reference. That gets you very negative outlook before starting on the competition. So make sure whatever claims you make, they're backed up by real references or valid references. And what we mean by that is peer-reviewed journals. The place you can get peer-reviewed journals is scholar.google.com. Most of those journals are free. The other way you can get valid references is talking to your professors in microbiology. You can use a microbiology textbook, geology textbook, paleontology textbook. Any of that is fine. Astrobiology textbook. Any of those are considered valid references. Okay. Another thing that's done is we ask for you to list all the instruments on the Mars surface missions and which are life detection or which are not. FYI, the only ones with life detection are the Viking landers. MSL doesn't have any life detection. Again, it's evidence of life, not actual signs of life, not actual life. Mir doesn't have any life detection capability. Pathfinder doesn't have any life detection capability. The Russians didn't have any life detection capability. Nobody that's actually landed on the surface has life detection capability except for the Viking landers in the 1970s. Then we also deduct for grammar, spelling, and lack of clarity in the writing. So all those are judges, or part of the things that we judge for the science plan. Usually teams do pretty good on the science plan, but you know, it's still some of the common mistakes they make. And we rank the science plans from 1 to 36. For the SARS, we kind of cluster them on, okay, this category is the best, this is the next tier, this is the next tier, and this is the last tier. For the science plan, we rank 1 to 35. 36, actually. Okay, here's the about the URC 2020 on-site mission. If you were able to make it and you got selected, congratulations. If you got selected, sorry you were not able to make it because of the COVID virus. So we had 3 different soil containers. These are about possibly half a meter apart, which was not wide enough. And some of these were baked, some were, we added organisms to it, and one of these was extinct, which meant it was, which meant it was, well, created from fossils, but that's all I'll tell you, because it's easy to guess what it is by that point. And then we had 2 rocks, a conglomerate and a limestone. The 2020 on-site competition, will be the same, except for these 3 will be farther spaced apart. There will be at least 4 rocks, and they will be spaced throughout this back section. So, because another problem we had is some of the rovers would run over the rock trying to get to the sample. So we're going to have it further spaced apart. And because we have more rocks for you to analyze, sorry, I don't know why that keeps changing. Because we have more rocks to analyze, you'll have between 20 to 30 minutes as opposed to 15 to 20 minutes on roving. So, yeah, it'll be just like that. You'll drive up to here. Try not to run into the sample. You can notice a wheel went into it. There, this one doesn't look too disturbed, and that one is just going everywhere. So between each team, we go out there and clean up the soil around it and refill the containers. So each team starts with a fresh surface on their soil containers, and these samples are clearly marked. So yeah, so that's what it looks like. And how it is, this is more of a close-up. If you notice somebody lost a drill bit in there, they got deducted points because that was considered contamination. But it's just a close-up of the containers, of the soil containers. Okay, so how 2019 was judged. Teams, for the briefing, you weren't expected to give a briefing with the Mars history, etc. We just take that information from the science plan now. And the teams needed to give their science results, which meant for each sample, sample 1, the team had to choose, is it extinct, or no life? For each one of those. They were scored on, did the teams get the correct answer, and was the reasoning correct? So a lot of these teams, for example, they didn't have any video feed or communications, so they, or they didn't have the camera available to look at their results. So there was a lot of different issues that had. So a lot of the teams, some of them just guessed. If you guessed correctly, you actually got some points. If you guessed correctly but gave the wrong reason, you got some points but not full credits. And vice versa, some of the teams guessed incorrectly but gave the correct scientific logic behind why they chose whatever answer. And while the scientific logic might have been right and the result wasn't, we still gave them some points. You only got full credit per sample if each answer and reasoning were both correct. Then you got full credit. And then we also deducted points if the team did anything to contaminate the loose soil samples. If you ran over the rocks, we didn't deduct the points unless the rock broke, but the rock didn't break. So we didn't deduct anyone's points for running over the rocks. We did deduct for running into the bin because you contaminate sample A from sample B to sample C. We'll be spacing the samples farther apart, so hopefully that'll be less of an issue. But if you did anything to the soil except collect it, meaning drop stuff in it, run over it, whatever, you got some points detected for contaminating the sample. Okay, so the most common mistake for the on-site science was trying to use, this is another thing. Some teams, although they said in their science plan they would have XY biology, a lot of the biology didn't work for whatever reason, or they couldn't see the results. And so they used the soil science, mineralogy, or geology to try to answer the question, is there life in the sample or not? That's not very good to do. Those can tell you habitability on context, but you actually need biology. You need to look for biomolecules to be able to say whether or not there is extant life in the sample. And then I explain why this is a not the best choice to use these. Now, all these are fine for context and for supporting evidence, but not as the sole science instruments. Okay, and then again, you need to search for life, which is biomolecules, and I'll explain what biomolecules are later. What I mean by molecules, what we mean. So the URC2020 science task was exactly the same as the 2019 with a few exceptions, and that's the loose soil samples are spaced farther apart and we'll add more rocks. That's it. The 2021 is going to be the same as the URC 2020 would have been. So you can look at the rules and regulations that are online and the question and answer document. The question and answer document provides a lot of clarification and insight as to what exactly we're looking for, a little bit more than the rules and regulations. Now, if there happens to be a discrepancy between the rules and regulations and the questions and answers, the rules and regulations takes precedence. Also, if you're reading the question and answers and it seems just so much more confusing than before you even looked at that document, you can email us for clarification. We'll answer to the best of our ability. Okay, here's what we think, or I consider, a biomolecule. So there's a lot of different things with biosignatures, biomolecules, bioevidence. There's a lot of different terms. I'm just going to use a broad term, biomolecule. That means anything that needs the presence of life to exist. Okay, so amino acids, for example, are biomolecules, but they're also found abiotically. So teams that are only looking for amino acids need to improve by adding another assay. Now, the team could look for amino acids and explain that they're only looking for the higher, more complex amino acids because those have only been found associated with biology on Earth. So if a team just said they're looking for amino acids but didn't explain that they were looking for larger amino acids and didn't say, oh, and we have these other methods to collaborate our results, that I considered those life detections, but I wrote a little note saying you need to include another assay. Okay, another thing is a biomolecular metabolite. So those use in metabolism, just like the word says. Adenosine triphosphate, NADH, flavins, etc. You can just very easily Google many of these things to say what is an amino acid, what is a metabolite. Also, biological pigments like carotenoids and chlorophyll. Those are seen with the naked eye usually and can be picked up spectroscopically. And then another classification a lot of people do is proteins, lipids, fatty acids, nucleic acids, carbohydrates, etc. Most teams that do well can detect multiple biomolecules. Again, you might want to do like a general Google search, so using Wikipedia to find out exactly what the molecules mean, and then looking what you've learned from there to go to scholar.google.com to provide an appropriate peer-reviewed article to substantiate any claims made in your SAR. All right, and then again, I want to reiterate that biochemistry and biology, not mineralogy, not soil science or geology, is what is needed for this task. The only Mars mission with a life detection capability for the Viking landers in the 1970s. Okay, here's another question for you, question and answer. You might submit a question and you have a lot of details to your question, but you get this not randomly, but you get a vague answer that doesn't fully answer your question. One of the main reasons is that you are expected to do the research to know the answer to your question. You might be provided a few hints, but if it's not clear enough what you need to do, you need to do that research on your own. That's kind of what is needed. If you don't understand what the answer even says, email it back. I don't even understand what you're saying. Can you give me a starting place? We will do that. Okay. Especially if you can't find any science members. We would expect I think every team, there are a few teams that do well in the science that don't have any science members, but they have also been coming to URC for many, many, many years and have learned what they need to do for the science. If you are a new team to this competition and you don't have a scientist on your team, you're likely going to do very bad in the science mission. Again, because you don't have the depth and the broadness that you need for the science mission. Because we will ask you questions during the science briefing and expect for you to know the answer. Most scientists will know the answer. Most engineers will not even know what we asked. Okay, so again, one of the goals of the URC is to simulate an actual rover on a planetary surface. So we're not going to provide you all the details. We want you to learn on your own, and we also want there to be planetary exploration part of this science competition. Every single mission we've sent to Mars or any other planetary body has sent back unexpected, unanticipated results. If we gave you how everything was going to be for the competition, it would take that exploration part away. Okay, and I think that is it. So thank you for listening to this presentation, and good luck with all your endeavors for 2020 and 2021. We hope to see you in May 2021. Back to you, Kevin.
Heather, thank you so much. That was a great presentation. And actually, I really love that last question that you had there, where you asked about the hypothetical question, why are some of the answers back to the teams a little bit vague in nature? And that's not just the case in the science mission. That happens a lot with some of the other missions as well, where teams will ask a question and we give generally a pretty vague answer back. And I think that's one of the unique things with URC is because we are very much requirements driven. And it's really about understanding what mission, what job needs to be accomplished. So exploration is confusing. It is uncertain. So sometimes the answers back are vague. Exploration is uncertain. And so I think it's important for teams to have an understanding of that when they're approaching URC. So
sorry, just want to let you know, Kevin, I turned the screen back over to you.
Thank you much.
You're welcome.
All right. So yeah, that was a great presentation, Heather. You really covered everything top to bottom. And we didn't have URC 2020 finals in the field this year. And as we start to think forward to 2021, one of the things that we're really concerned about as judges is making sure that continuity of knowledge is able to transfer over to the new teams. So that the new teams in 2021, by the time they get to the field, they may not have been to the competition for 2 years, and even for new teams. There's always new teams each year. So it's important to get a lot of this knowledge out there so that everybody has at least some understanding of what to expect out in the field.
Yeah. Can I add something there? We had a score sheet for 2019, and we intend to have a very similar score sheet for 2021. We'll just add some more rock samples because we only had 2 blanks for rock samples since we only had 2 rocks out there. We'll have, 4 to 10 rocks out there for next time. Other than that, the score sheet will be very similar, and all of the judges for 2019, it might be the same judges for 2021. We're not completely for sure, but there should be a lot of continuity between the 2019 and the 2021 competition. And also, if you competed in 2019, we can send you your score sheet, and we will not post the 2021 score sheet or let anyone see it, the exact score sheet, prior to the competition. And another thing is when you go out to URC, if you're lucky enough to get selected to go out to URC, you're not allowed to see the science site prior to your competition time. And you might be wondering why. One of the main reasons is when the rover lands on a new planetary surface, it's the first time the rover and the scientists are seeing that planetary surface in that location. So for the science mission, we want to keep it that way, where it's the first time the rover and the science team is really able to evaluate that landing site or that science site. Second reason is if you went out there as a human and you walked around and looked at the site, well, you could already figure out all the data with your human eyes, not using the rover. And so that takes apart some of the spirit of the competition. And the third reason is if you have the science on the last day versus the first day, there's differences in the ability of the team to be able to make it to the science site. So Maybe you show up, the day before or the morning of at 3 in the morning and you're competing in science. Well, you didn't have time to go see that science site. So we just don't let anyone see the science site prior to the competition. And if your family shows up, we also ask that they don't walk all over the science site, because that looks very badly for your team if your spectators can't even obey the rules. So again, you won't be able to see the science site prior to the competition. Now you can look at images online. You can look at orbital. It's another thing. You can look at a lot of the past competition stuff. I think there's a Facebook website, and also you can look at satellite imagery of the sites. That's something that a lot of teams do prior to coming. Is they do a lot of research prior, with the science mission in particular, prior to showing up at URC. Almost all the data, actually all of the data that is required for you to do well for the science is free. Excuse me, with the exception of your scientific payload. But the research shouldn't cost you any money. So it's not really a matter of one institution has better finances than another. It's a matter of, did one institution take the time to talk to the scientists to figure out how to get the data or not? And we have had some of our best teams have been from very low budget schools, or they've had a very low budget for this rover challenge, and they've done very good on the science.
Yeah, absolutely. Those are all excellent points, and certainly, it's important to understand what resources there are, what research you can conduct ahead of time. But when it comes time to actually conduct the mission, just like with a real Mars rover, the first time you get to experience any of the environment or any of the prospective samples are through the cameras and various sensors of your rover. So it's very analogous to real world exploration context. So Heather, thank you very much. Really appreciate you taking this opportunity. For all the teams that were watching, thank you very much for watching this. We really hope that this is helpful as you start to plan for your 2021 missions. And with that, wish everybody a great day. I'm Kevin Sloan with the University Rover Challenge, and we will see you all later.
Thank you.